right, so in today's video, we are going to be beginning chapter 11 on waves and oscillations. So we get to take a little bit of a break from some of the heavy stuff that we've been doing lately with electricity and magnetism and cover some stuff that's a little bit more fun. So I think probably we are past the most conceptually difficult part of the semester, and the rest is usually a little bit more fun. It feels quite a bit more tangible, right? You can see these things in your life, you experience them in your life, and I enjoy it as well quite a bit more. So let's get started. So today we're talking about oscillation and waves, and so this is chapter 11 in your book. So we're going to start off talking about simple harmonic motion, and then we'll introduce some basic properties of traveling waves. Okay, so to talk about simple harmonic motion, we first need to remind ourselves what some things about springs. Okay, so way back in the day, we talked about springs. So I have a spring right here. So here's a spring, right? And if I pull on it, there is a force that is attempting to return that spring out like that, right? So the spring in its undisplaced position wants to be like this. And when I stretch it out, my thumb now on the bottom is pulling down. It's exerting a force to counteract the spring force, which always wants to pull up. So the number one thing to remember about springs is that the direction of the spring force always points into the undisplaced location of the spring. Okay, so and there's a formula that goes along with that. So the spring force depends on the spring constant K. It has the units of newtons per meters. And this is a measure of how springy the spring is. A really stiff spring has a very small spring constant, and a very stretchy spring has a really big spring constant. I might have said that backwards. Don't rely on me. The spring constant depends on the stretchiness of the spring. And then it also depends on the displacement from equilibrium. Okay, so what I mean by that is here is my spring here, and I'm just going to take this up here and maybe draw it a little bit. I'll draw one more here, which is our undisplaced spring. Looks like this. Okay, so right, this is my undisplaced spring. So putting it like this, not stretching, this is an x naught of delta x of 0. Okay, so here is delta x equals 0. There's a small displacement from the equilibrium position, and there's a bigger displacement from the equilibrium position. Okay, so and this negative here, you've heard me say it several times over the course of the semester, I don't love this negative. This negative here is a negative that tells you that the direction of the spring force is always back toward the undisplaced position of the spring. So what I mean by that is, right, delta x points to the left, which must mean that the spring force points to the right. And as you've heard me say many times, I prefer to just use your brain to figure out the directions of things rather than rely on a formula to tell you. But that's what this negative here is for, to tell you that the direction is opposite the direction of the displacement vector. Okay, and you can also have springs that are, say, like this. So you can squish springs as well. I can't so much squish this spring, but if you think about a stiffer spring that sort of has like this as its natural position, right, you could push on it and make it be stiff. So this here would be a different delta x, right? And that displacement would still be the displacement from equilibrium position, and you'd plug it in as a positive number, and you'd take into account this negative sign to here to say that the spring force would point now to the left in the direction back toward the equilibrium position of the spring. Okay, so another something that we have talked about, but not for a really long time, is frequency and period. So period is the most conceptually intuitive number. This is period, which we abbreviate, of course, with a capital T. We haven't used that one yet, so I guess it's not a terrible one to use. The period of a spring of any oscillation is the time to complete one full oscillation. So this is a heartbeat monitor. So the period here would be the period between heartbeats. If I have my spring right here, and I displace it, you can see that it starts to oscillate a little bit. It would be better if I put a little mass on it. It starts to oscillate a little bit. You can see it going up and down and up and down. That up and down, the time down, down, the time when it gets back down to its equilibrium position. That's the oscillation of the spring, the period of oscillation of the spring. So we measure that in the units of seconds, and we abbreviate with a capital T. The number of cycles per second is the frequency. So we abbreviate that with a lowercase f. And you can see from this formula here, where the frequency is 1 over the period, the units are 1 over seconds. So you can think of units as being 1 over seconds. But usually we don't write it this way. We write it as seconds to the negative 1 power. You might have also seen this unit here, hertz. You've probably heard of hertz. Actually, I can hear what 60 hertz sounds like in this room. I'm not sure if you can hear it. That buzzing sound that is present in rooms when they are there, that's because our outlets run on 60 hertz oscillations. So they make 60 of these every second. And if something that is oscillating at 60 cycles per second is, say, bumping up against something and vibrating, then it can initiate a sound wave that you can hear. So that's what frequency and period are. Okay, so now that we've got a couple of fundamentals, let's throw in some more complex equations. If you don't have your equation sheet, now would be a great time to pause this video and pull it out, because I'm going to get my equation sheet out as well. There are a lot of equations on oscillations in our equation sheet. Here's the page. So I have some things, right, that we've already talked about. So here's the equation, frequency is 1 over period. I think that's about all that we have right now. But basically all these equations are equations for chapters 11 and 12. No, basically about it. This whole page is for chapters 11 and 12. We'll talk about waves, and then chapter 12 we'll talk specifically about sound. I'm going to really treat chapters 11 and 12 as one long chapter that we'll cover continuously. So the distinguishment between those two chapters is not really that important to me. One equation that is not actually on here, so I'll have to think about, oh, there it is. It's right here. Is that we know from a long time ago, and so this would be an equation that was from last semester, that we can say that the total energy in a system is the kinetic energy plus the potential energy. And of course, this would ignore any non-conservative forces like friction or air resistance that might remove energy from the system. But as long as we can consider this system a closed system that's not letting energy escape out into the room, then the total energy is these two together. Kinetic energy we already know is 1/2 mv squared. So we'll plug that in for that. The potential energy of a spring is this formula right here, which is 1/2 kx squared. And this would be a good little note to write on your equation sheet, because I didn't actually define the potential energy of a spring, but right here, that's kinetic energy. And right here, that's potential energy. So this is energy of a stretched spring. Okay. And I wanted to talk about what happens to the energy of a spring as it undergoes what's called simple harmonic motion. So I'm going to demo in a video that I'm going to show you about this. So let me move over here. Okay, so let's get this out of the thing. I'm not sure how well you can see this, but right up here is springs. So I have a cart here that's attached. It's on this track that you'll recall from lab last semester, and it's got strings pulling on it in both directions. Okay, so I can displace this cart, and it will go back and forth like this. So this is a nice way to visualize what goes on with energy. Okay, So when I have stretched it all the way out as far as it can go, it's not moving. But it does have energy. The kind of energy that it has is the kind of energy that's associated with the potential to do damage. Remember, I like that definition of potential energy, right? If I let this go, it'll do some damage. And the farther I displace it, now it's out of your screen, right? The farther I displace it, the more potential energy or the ability to do damage I give to it. Okay, so when I'm out here, I want you to kind of think about how fast this sucker is moving when it gets to here, its maximum displacement, okay? So as I let it go, right there, there's this momentary period of time, just like with the pendulum, where it has to switch between moving this way and moving back this way. And that period of time, right at that instant, there is no motion of this thing. Okay, so it is all potential energy. Potential, all potential, all potential, all potential, like that. So we're going to give it a certain amount of energy, and it's going to maintain that certain amount of energy, but the energy is going to be constantly sloshing back and forth between the energy of ability to do damage, that's potential energy, and the ability, the energy of motion, which is kinetic energy. So I want you to think about where there is the most kinetic energy when I move this thing back and forth. So there will be the most kinetic energy when it's moving the fastest. Okay, it's clearly not moving the fastest out here, but what's going on with this thing is that it's stopped, and now it's going to go faster, 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 faster until it reaches its equilibrium position, and then it's going to slow, 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 slow until it stops. Faster, 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 faster. Right here in the middle of its motion is where the kinetic energy is the most. So kinetic potential, kinetic potential, kinetic potential as it goes back and forth. And of course, when it's neither all potential or all kinetic, that's a period of time when it's a mix of the two. And I think I'm actually not going to show the video I was thinking about showing, because I think that kind of covers it. The video is pretty repetitive with that. Okay, so, and this is a figure from your book that's showing you what I just showed you, right? So we have all potential, so the total energy is 1/2 K times the displacement squared, where, what do you think A must stand for? A here is the amplitude of the oscillation. Right, so this should be 1/2 K times the displacement squared, but when the displacement is at its maximum, we call that the amplitude, is the maximum displacement. Of any oscillation. So I'm talking about this with respect to springs, but the same would be true for pendulum, or any number of oscillators that goes up and down. We're going to specifically talk about springs and pendulums, so those will be the two we focus in on quantitatively for this chapter. So that energy is all potential, so its energy is all the formula for potential energy. Down here in the middle, the energy is all kinetic, so the amount of energy is 1/2 times v mv squared, just like the formula for kinetic energy, and it goes back and forth like this. Okay. So let's talk about the potential the energy of springs a little bit more quantitatively. So high frequency, this is something that bounces up and down very quickly, like this. Okay, so a high frequency, right? There's my formula for frequency. A big frequency must be a small period. Okay, so as f gets bigger, period goes down. So take just a second to think about this. Okay, so here's my spring that can go up and down, and it goes like this. And I want to just think about what happens to the period of the spring as it goes up and down. And now I'm going to put a mass on top of here. I don't want that one. I want this one. So I'll put a mass up on top of here. Do you see how it got slower? So the period of oscillation has gotten longer. So T has gone up as this thing has more mass on it. So there's with no mass. Maybe we can super exaggerate it with this huge mass here. Yeah, so it goes up and down really slowly with this big mass. And I put on the smaller mass. It's going up and down, but it's not going up and down nearly as quickly. All right, so what has happened here is that there's two things that determine the frequency of period of the frequency here, which is the spring constant. So this is how stiff the spring is, and also the mass. Okay, so as we added more mass, right, it went slower. Okay, so I could say as I added more mass, what happened was it was slower. So that is that T has gotten bigger, right? The time to complete one oscillation was more than it used to be, okay? If this number here in the denominator gets bigger, then that must mean that this number over here in the numerator gets smaller. And that's exactly what we observed, okay? So it took longer for the period, which meant that it was going up and down more slowly, and that is a low frequency. We'll get a little bit more quantitative with this frequency versus period distinguishment. But for most people, it's easiest to think about period, right? As period getting bigger when something takes a long time, because I think in terms of seconds very easily. I don't necessarily think in terms of frequency very easily. What is not in here is amplitude, okay? So if I think about displacing this a little bit, and if I displace it a lot, or a little bit, the period stays the same. So it's going up and down with the same frequency for a big amplitude displacement or a small amplitude displacement, okay? And that's going to be a theme of pretty much all of this next couple of chapters, is that amplitude really doesn't matter, okay? So let's see if you were paying attention. So I'll try to work on this one. All right, so the answer here is D. So let's talk about why. So let's pull up the formula from the equation sheets. And now I'm going to look at these two equations right here. So this is the one that I put on the previous slide that says the frequency is 1 over 2 pi square root of k over m. But this question is actually asking about the period. So I'm going to copy down the formula for period. T is 2 pi square root of mass over k, the spring constant. And see how these formulas are almost exactly the same formula? They come from this relationship here, which is that frequency is 1 over period. So all that I've done to this frequency formula is flipped it up and down, upside down. Right? The 2 pi was on the bottom, now the 2 pi is on the top. K was on the top, now k is on the bottom, m was on the bottom, now m is on the top. That's the only difference between these equations. Okay, so we have this formula right here, which is the one that we're interested in. And we will say that the initial period is 2 seconds. So, so T1 is 2 seconds, and T2 is going to be 2 pi times the square root of m over k. And now I'm going to think about how does m change and how does k change? K stays the same, so you can plug in whatever number you want for K, and that should be fine. Or maybe, I don't know, if you want to do this with numbers, you're probably going to have to solve for what K has to be so that it matches this 2 seconds number here, which might be a lot of work, but totally doable. What I'm going to do here is that I'm going to say that this mass is twice as big. All right, so this mass is twice as big, so I plug in a 2 here. This one right here was 2 pi times the square root of m over k, and this one was 2 pi times the square root of 2m over k. The only way that these things are different is by this factor of a square root of 2. So let me factor it out. So this is 2 pi times square root of 2 times the square root of m over k. So all I've done is pulled out that square root of 2. And this should be, hopefully, let's do this with numbers so I can convince you that you can do this with algebra. So if I have the square root of 2 times the square root of 4, or square root of 2 times 4, that would be the square root of 8. I probably should have picked a better number. Let's do the square root of 4 times the square root of 4 so that we can actually calculate this in our head. So 4 times 4 is the square root of 16, which is 4. If I instead say this is the square root of 4 times the square root of 4, then I'm going to say, well, square root of 4, that's 2. Square root of 4 times 2, and that's 4. Okay, so it's totally fine to split this apart. And that means that T2 is just the square root of 2 times whatever T1 was before. So I'm going to take this factor of square root of 2. T1 before was 2 seconds, and the square root of 2 times 2 is square root of 2 times 2 is 2.8. So I got 2.8, circled it. There we go. Okay, so a couple of cool things about simple harmonic motion. So this is simple harmonic motion that we've been talking about so far. I haven't been great about defining that. So simple harmonic motion is this kind of motion that goes up and down continuously. So any situation where we have this sloshing of energy back and forth between kinetic and potential and kinetic and potential, that is what defines simple harmonic motion. Okay, so this cyclical motion that goes back and forth like that. Simple harmonic motion is really similar to motion in a circle. So if I have uniform circular motion, I can think about that as being really similar to simple harmonic motion. And let me show you what I mean by that. So I have here a turntable, and on this turntable, there's a styrofoam ball connected to it, just so that we can see what's happening. So I want you to watch the motion of the styrofoam ball, and you can see something going around in a circle, maybe, going in a circle like that. So it's going around in a circle. That's kind of what the circle looks like. And if I put it like this, it now no longer looks like it's going around in a circle. But what it does look like is exactly a simple harmonic motion, okay? If you think about this as maybe being similar to this thing going back and forth, I know they're going back and forth at different speeds, but what we said was that over here, it stops, right? It's all potential, and then it's fastest in the middle of its motion, and then it stops over here. And if you watch this for a second, can you convince yourself that it's true? Slow, fast, slow, fast, slow, fast, slow, fast, slow, like that. So it's this thing that seems like it's speeding up, slowing down as it goes back and forth like that. You can get a really fun party trick. I know that we're all home, cooped up in our houses right now. Watch the microwave. What your mom told you wasn't right. Microwave's not going to burn your eyes. It's not going to fry your brain. Microwave's totally harmless. So you can watch the microwave and just know that you're watching some simple harmonic motion. It looks like simple harmonic motion, but it is actually something going around in a circle. Whoops. Okay. And just to drive this home again, I have a video I wanted to show about that. So we will see if we can make it work. There we go. Not you. You. So here is the motion of a ball going around in a circle and also superimposed against the motion of the spring going up and down. You can see that actually the motion of those two particles track each other almost perfectly. Well, no almost about it. They track each other perfectly. All right. Okay, so let's keep going. Oh, yeah, so there's a reminder. You can track simple harmonic motion in your microwave. So fun times in dark days where we're all stuck at home looking for exciting things to do. I'll try to give you as many party tricks as I can. It's not as party tricky of a semester as it was last semester, but we'll work on it. All right, so we got springs. We've talked about springs. Now let's talk about a pendulum. So a swing is a pendulum. A pendulum is just something that goes back and forth on a string. I have a spring. Let me grab it. So here's my pendulum. It goes back and forth on a spring, just like that. There we go. Something that maybe you haven't appreciated before, but I'm sure that you know, it's true for a spring as well. This thing only wants to go back and forth at one frequency. Maybe it struck you as strange that for this pendulum, for the spring, there's only one frequency, but no matter how hard you try, you can't make this thing go at a frequency that it doesn't want to go at. Same with the spring. So the only thing that affects the frequency of this spring or the period of this pendulum as it goes back and forth is the length of this spring. Not even this mass right here. It's a pretty big mass, or at least a big in volume mass. If I had a teeny tiny little mass, even that mass wouldn't matter. The only thing that matters is the length of the spring. So let me see if I can show you. See how it got slower? When I make this shorter, it gets faster. That's the only thing that matters. And the equations show that too. So here's the equation. The equation is that the frequency of a spring depends on this 1/2 pi factor, just like it did for a spring. The length of the spring, I keep saying spring. I hope that you know that I mean pendulum. Sorry about that. So this is the length of string. And also G. So maybe you can even think about like astronauts walking on the moon. When Lance Armstrong is saying that's one small step for man, you see him jumping and he was jumping and he looked like he was jumping really slowly. That's analogous. Of course, Lance Armstrong was not a pendulum on a string there, but if you took a pendulum on a lower gravity location, that would also affect the frequency. So I said only one thing matters, but I guess I was lying a little bit. Technically, two things matter. If you take this to another planet, the frequency will change as well. Another thing that's not in here is amplitude. And we already talked about how mass isn't in there. And again, those equations are on the equation sheet. So here's the equations for pendulum. And this is probably too small for you to read, but hopefully you have your own out. So I have the two equations for period and frequency. And just like they were for the spring, those two equations are just flipped upside down versions of each other. All right, there you go. So give it a pause, and when you think you got your answer, unpause it. And the answer here was A. Okay, the only thing that matters is the length of the string. So the smallest string will go back and forth at the same time. Okay. Oh, it's not really. You have any swing sets in your backyard? Probably not playground friendly right now, but if you have swing sets in your backyard or a playground that nobody visits and you want to break some rules, you can try this. Like a 300-pound linebacker for the Kansas City Chiefs would swing back and forth with the same period, more or less, as my 35-pound 6-year-old. So, you'll often see when you see people on playgrounds, they go back and forth. It's always kind of surprising to me, and I've verified that this is true many times in my life. I encourage you to do it as well. Right? Mass doesn't matter. You go back and forth with the same frequency on a swing, even for a heavy person versus a light person, and even for somebody that's going with a big amplitude and somebody who's going with a small amplitude. I guess I should warn that this isn't totally true, that there's no amplitude in it. When you get to really big oscillations, the equation that this is based on sort of relies on, it kind of breaks down a little bit. So this is an approximation. It doesn't work for really big oscillations. So it won't work for really big ones, but it works for most of them. Okay. Let's design a pendulum for a clock. So grandfather clock is designed so that one swing of the pendulum in either direction takes 1 second. What's the length of the pendulum? So let's write down what we know, which is we want L, the length of the pendulum, and we know one swing is 1.00 seconds. Okay, so what's that mean the period is? I'll give you a hint. This is a little bit of a trick question. It's not 1. The period is 2 seconds. Do you see why? Here's my grandfather clock. Okay. It says that from here to here takes 1 second. But the period is the time to complete one complete oscillation. So we want the time here and back. Okay. So the whole time for a whole oscillation is not 1 second, but 2 seconds. All right. Now we'll pull up the formula for the period of a pendulum. T is 2 pi, the square root of L over G. And I'm being a little bit lazy with capital L's and lowercase l's, but we want the length of the string, whatever it is. If I call it a capital L or a lowercase l, which means that I need to solve for L, which is underneath the square root. At least it's not in the denominator. You will have to solve for things that are in the denominator, but here we go. So how are we going to solve for this? When you want to solve for an equation, you isolate it by itself on one side of the equation. So let's start off by getting this radical all by itself, or as by itself as we can. So I'm going to divide both sides of the equation by 2 pi. Okay, so now my 2 pi's cancel, and I'm also going to flip this so that I can have my L on the left-hand side. So I'll say that the square root of L over G is T over 2 pi. Okay, now if I want to get rid of this square root, I need to square both sides. So I'm going to take this side and square it, and take that side and square it. Okay. Now this side, I have a square root squared, so now I have L over G like that by itself. And now I have this whole thing is squared, so this is T over 2 pi squared. You can leave it like that, and that's just fine. I don't love looking at things like that. So I'm going to go ahead and distribute this squared. So I can say that this is T squared over 2 squared, which is 4 times pi squared. Either one of these would be just fine, but just so you can see how to distribute that square. I've still not fully solved for L, but at least I've gotten rid of the square root. So I'm done with the square root. Now, if I want to get rid of this G, I can go ahead and multiply both sides of the equation times G. And now I have a G on the top and a G on the bottom, so that cancels. And this right here is my full answer, which is that L T squared over 4 pi squared times G. If you don't like this being out to the side, that's just fine. A similar way, or a mathematically identical way to write this would be T squared times G over 4 pi squared, something like that. All right, now we've solved for L, we're ready to plug in numbers. I've got the T is 2, so this will be 4, 2 squared times 9.8 divided by 4 pi squared. 2 squared times 9.8 divided by 4 divided by, this is a new calculator to me. Where's pi? I don't know. I'm just going to say 3.1415926. Don't we all have pi squared pi memorized? Okay, and there we go. 0.993. I ran out of space, so I'm just going to write it over here. Equals 0.993 meters. How many sig figs do I want? I was given this many sig figs in my problem, so that's 3. So I want 3 sig figs in my answer, and there you go. You ever wonder why grandfather clocks are always big? This is why they're big. Because in order to get this sort of a period of oscillation, you need to have something that's almost a meter long in order to have it happen. So a meter is about 3 feet. So you need a grandfather clock that's pretty hefty in order to fit it, in order to have that work. Okay, here's some more applications of the period of oscillation being dependent only on the length of the pendulum. Right? How do you hold your arms when you walk? When you walk, you probably hold your hands straight out. See if I can find a way to get me all in here. Right, you walk with your hands straight out like this. And when you run, what do? You run like that. What you are doing is making your arms shorter so that the natural period of oscillation can be faster for your faster gait when you're running. A really fun thing to do, this is all coronavirus friendly, would be to try to run while holding your hands straight. It's very hard to do. What's another thing that we do is when we walk, right, we hold our legs pretty straight. But so we walk like this, right? When we run, we bend our legs. The reason that we bend our legs is to make our legs shorter so that we can have a faster gait because our leg pendulum is shorter than it used to be. All right, we're going to stop this video and we'll start the next one in a few minutes.